The next topic we're going to cover in business analysis is linear correlation and regression using one factor. We'll go through terminology with it, and then we'll go through an example as well as some precautions. So linear correlation and regression with one factor basically means that we're going to be comparing two items. So for example, how much we spend on advertising, does it impact how much we make in sales? How much the weight of a product is in comparison to how much it costs to ship it? So we have X, Y variables that we can assign to those and do plots to go along with them. So in these, since we're using linear, we can actually see some of them. So we're going to try and keep it simple using plots and graphs along the way so you can see the meaning of some of the terminology behind what we're doing. So correlation coefficient. Does the graph of the plot look like a line or does it look completely random? So again, because we're using linear and we're using an XY plot, not XYZ or other factors to go along with it, you'll see in the first one, yes, it very much looks like a line. The second one, you can see where the line is, but not everything's going to fall on the line. And the third one, I can't quite figure out just by looking at it where the line is going to go on there. And I can't see that many points will fall near the line either. So the correlation coefficient is denoted by R, or rho, which is your Greek R. It looks like that small p. R is for a sample, rho is for your population. R will range between -1 and +1. It has a different meaning whether it's closer to -1 and +1 than it does if it's closer to 0. So the closer the number is to 1 or -1, the higher the relationship, the higher the correlation. In simple linear regression, in simple terms, the closer the plot looks like a straight line. If, for example, is closer to 0, there is no correlation, and the plot looks more like a random spattering of points. So if I look at these, R is 1, definitely looks like a line. R is 0.91. You can see how it's close to 1. Not everything's going to fall on that line then. 0.04 is awfully close to 0. So in this one, there is no correlation, and the plot definitely looks more like a random spattering of points. So when they look more like the first two, you can help start using prediction on those. But when they look more like the third one, you can't really use prediction on those. Next bit of terminology, simple linear regression model, or the regression model, or the least squares, or there's lots of different ways to say that one. What is the line of best fit? You're trying to minimize the error in the plots found off the line. In college algebra terms, y equals mx plus b. M is the slope, b is your y-intercept, your constant. And so when we look at those in terms of statistical, we just flip the two of them and call them beta sub naught and beta sub 1. But they have the same meaning. So we're going to stick with the college algebra method to go along with it. So we'll see that the line that goes along with these, and these are not the same graphs as the previous ones. So the first one, they definitely look more like a line. You can see where they're a little bit off the line. Second one, yeah, that one's pretty high on there. And then the third one, again, they're looking a little more kind of scattered. So if we go back to what we were just doing in the previous one, a little bit of practice on that one, I would think that the R value, remember they're closer to 1 when there is a relationship and closer to 0 when there's not. I would think the R value on the first two is going to be closer to 1 or -1, and on the third, closer to 0 than to 1. So when we look at those, we will find that that indeed is the case. The other thing that you will find is that when the slope is positive, when it's going upwards from left to right, the correlation coefficient is also positive. When the slope is negative, it's going downhill, then the correlation coefficient R is also negative. So when we're looking at these, 0.91, negative 0.97, close to 1 and close to negative 1, negative 0.37 is definitely closer to 0 than it is your 1 or negative 1. So on the first two, looking like we have good models. The last one, probably need a hypothesis test to show if there is any validity to the relationship. So your linear regression model is really that equation. Y equals 9.7x plus 460. Y is negative 372x plus 14,871. Last one, y is negative 0.0157x plus 54.2. That's your linear regression model. The coefficient of determination, how much of the data is explained by the correlation model? What percentage is what we're going to be converting some things to on this one. So coefficient of determination is noted by r squared. To find r squared, you simply take little r, your correlation coefficient squared. So looking at the previous three graphs, we're going to find that 0.91 squared got us a positive 0.82. Negative 0.97 squared is a positive 0.94. Negative 0.37 squared is positive 0.1369. So r squared, because of the squaring of it, will range between 0 and 1. And just like your correlation coefficient, the stronger it is to 1, the stronger the relationship or correlation. And the closer it is to 0, the weaker the relationship or correlation. So how do you use the coefficient of determination? So the coefficient of determination, we have our r squared value. So 83% of the variation in y can be explained by knowing x. 83% is a pretty good number. 94% of the variation in y can be explained by knowing x. I like 94%. The last one, 13.7, so 14% of the variation in y can be explained by knowing x. 14% is not a very high model. So again, in looking at this, these two seem like stronger models, and this one does not seem to be a strong model. Prediction. So using one of the plots from the previous one, does the model have meaning? So as much as we like to use the r squared value or the r value, it's nice to have that hypothesis test to go behind you to say, yes, we can statistically say it does have meaning. To do that, you can do a test on the correlation coefficient r. You can use a test on the beta 1 test. There's several different ways to do this one. We're going to use the simplest non-number crunching way and letting Excel crunch the numbers for us on this one. So in Excel, when you run the regression piece of it, there's a place where, and I'll show you a few slides from now, there'll be a place where it says the significant F value, which is really a p-value. So you're going to compare that to your alpha. If p is less than alpha, then the model is significant. So in our example, let's say we're trying to show that the model is significant. So is or is not is a two-tail test, equals, not equal to. So if alpha started as 0.05, you're going to divide it in 2. Therefore, we're going to find that's 0.025 in each tail. Because 0.0153 is less than 0.025, the model is significant. So we're not just basing it off our R values. We have shown that the model is significant. And if there is a significant model, how much variation can be explained in the variables? So in this case, 83% of the variation in y can be explained by knowing x. Pretty comfortable with that one. Precautions. So when you do this, it's fairly important. The prediction model is limited to values within your sample area. If X in your sample goes between 120 and 183, you shouldn't use the model to predict the value of Y when X is 200 because that's outside your sample values. So if we use, for example, advertising and sales, if we spend between 120 and $183, we don't want to say, well, what happens if we spend $200? That's not within our model. So the model might give us a guesstimate, but it's not meant to give us a true, fairly accurate meaning of. You can't say we're 83% there. So don't assume that there's a causal relationship is the next point. So because we're going to spend money on advertising, it doesn't mean that it's going to cause sales. Money spent on advertising influences sales, but there's a lot of other factors that cause sales. Another factor, precaution, model is based on a sample or samples. Next time we do it, might not get the same results back out of the equation. This is point here, that if the model has a high R-squared value and a large standard error, the model may have limited application. That's included in this slide because I don't want you to think, oh, that one has an 84% R-squared value, I'm good. There's other factors that need to be checked, so just kind of in the back of your head, don't be sure and check all the boxes before you start making assumptions. You might have a limited application for it. And last but not least, hindsight's 20/20. It's only after a model is used and tested do we really find out how valid it is for prediction. If these were valid all the time, we wouldn't need managers, right? We would have software that could tell us these things. So we need that human aspect to go along with it. A perfect example on that one is we're planning on spending money on advertising, but I know that next month they're going to be doing construction right around my store. So even though I am out there and spending money on advertising, my sales are going to take a dip. It had nothing to do with the fact of what I was spending on it. So it's only a prediction as long as other factors around it seem fairly constant, and that's where it takes that human factor to help with. So let's do our example. So weekly sales data is recorded along with the advertising spent on that week's ad. The data is run through Excel with the results shown. So we come up with our graph, and we also come up with our summary output from Excel. So in looking at this, we can see, ignore that the line is there, we can see from the spattering of points that it appears that it would go around a line fairly well. We can see from our R-squared value that 84% of our variation in sales can be explained by knowing the advertising. We know that our R value is 0.91, and we know it's positive because the slope is positive. We know our R-squared value is 0.835, as it shows over here as well. We know the equation for the line is $9.71 X plus 472.62, and our significant F value. So there was that value we were talking about. This one is written in very interesting terms because I have a 1.82 e to the -8th. So scientific notation means you're going to move that decimal place 8 spots, so you're going to have 0.00000, whatever, 0.182, a very small number at any rate. So if the p-value is less than alpha, there is a correlation. So in this case, I could pick 0.01 for my alpha, and there would be a correlation to go along with it. There are some other things on this slide, but just kind of the highlights of it. It's fairly easy to get the equation, fairly easy to see your R and R-squared values, and fairly easy to see if your model is significant. So let's walk ourselves through that step by step. So first thing is to graph it. So decide which is the independent variable and which is the the dependent and the independent variable. So Y is the dependent one. Y is what we're trying to predict. So weekly sales data is recorded along with the advertising spent on that week's ad. We're trying to predict weekly sales by knowing advertising spent. So Y is sales, X is advertising costs. Y goes along your vertical, X goes along your horizontal. So we're using advertising to help predict sales. Another way to do that is, does knowing advertising help estimate how much we'll make in sales? One would hope so, right? So develop a scatter plot for it, which we show to the right, but to do that in Excel, one of the things to be sure of is make sure that X is in your first column and Y is in your second. You don't have to do that, although it is very helpful if you're just using the quick button clicks through. If you do it the other way, you'll end up predicting advertising off of sales, which wouldn't make a whole lot of sense. So in Excel, click on Insert, Scatter Plot, and then format it. One of your predetermined options is one that has the equations in there, so just play around in your formatting for your graphs. And as soon as we do it, graph it without the line there. Does there appear to be a correlation to a straight line? Yes, there does. So step 2. So we've plotted it. Looks like there's a line. Step 2, correlation coefficient and the test to go along with it. So our slope is positive, so it means R is positive. Our R value is 0.91, and it's positive because the slope is positive. Is it significant? So is that value, is that p-value less than alpha? If so, there is a correlation. So because 0.000018 is less than 0.2025, there is a correlation. Had we found that our significant F value there was 0.048, which was probably the case of, remember that third graph on our previous ones where that third graph was always, looked like more spattering of miscellaneous points than actually a line. So that would be there would be no relation. There would not be a relationship between them. So, but in this case, there is a relationship. So fairly easy to see what the R value is and what the relationship is. The coefficient of determination is there. So approximately 83% of the variation in sales can be explained by knowing the amount spent on advertising. So 83% of the variation in sales, how much up and down we go, can be explained by knowing how much is spent on advertising. The next piece of it is one that we'll go ahead and use a little bit less than others. So it's a slope and its confidence interval. There are actually 3 confidence intervals that we can have in regression analysis on this one, and we'll go through all 3 of them. The first one is on the slope. So if we just take the very simplistic version, we're not going to plug any numbers into the equation. We're not trying to predict Y from a specific sales point right now. We're just trying to look at the slope by itself. So the slope is 0.9 or $9.71. The book in your example talks about it. Can you explain what the coefficients mean in the regression model? So your slope means that for every dollar increase, since this is in dollars, for every dollar increase in advertising, sales is increased by $9.71. So for every dollar increase in advertising, sales is increased in dollars by $9.71. Because that really is what helps predict the line, we can see that not everything falls on the line. So the slope of the line could be a little bit different. The next time we did a sample, we might find that the slope of the line is different. In fact, we probably would. And so what would that slope range between if we had several weeks in a row? It would range between the confidence interval on the slope. So based on a 95% confidence, we estimate that for every dollar increase in advertising, sales increases between $7.57 and $11.84. So if you're a little more of that conservative manager, you could go with that $7.57 mark and you would have a very conservative value for your estimates. The $11.84, that's when you think things are going to be gung-ho. So that's those other factors that you can use to determine, what's your traffic flow going to be at your restaurants or your store, and other factors that go along with it. So there are pieces that make that adjust a little bit. So the next piece of this is the regression line and prediction. So if I spend $310 on advertising, how much am I going to have in sales estimated? So when we do this, what we're going to do is we're going to look at the slope of the line. So we're first going to see if it's valid before we do that. So our p-value for that, again, is less than alpha. So therefore, beta 1 is a factor. The reason I point that out is because if we're doing sales and advertising on this one, we could also use, let's say this is in my restaurant's in a downtown area, and I'm going to say that when we go ahead and look at how far my restaurant is from where people are coming from, so from work. So we could say how much we spend on advertising, how far people have to travel to get there, whether it be from work or from home, and there could be many, many other factors that you throw into that one. And so based on just advertising alone, what can we do with it? So we have our alpha value for advertising is less than 0.025, so we can use it as a factor. If we had other factors in there, we might find that they're not significant. We know that the model itself is valid because the significant F value is less than alpha. And so our equation is here, which is also noted over here. So how can you use that for prediction? So if we write the equation, we know that the range of x from our sample goes between 105 and 605. So let's go ahead and say $310 is spent on advertising, which is within our range. If I would have tried to say 700, we couldn't have used this model for it. So if $310 is spent on advertising, it looks about 3,500. You plug that into the equation, you come up with 3,482.72, rounded up to 3,483. So the point estimate for sales is 3,483. Now notice most of the points don't fall exactly on the line, so there's going to be a confidence interval around these right here that we could look at, that we could use to get our high lows on that one. Excel doesn't have a natural way of doing this. You can use macros to write one. In this case, our class has a program called pHStats because it's provided by our publisher, and they can help us with prediction along these lines without crunching a lot of numbers. So we're going to just go ahead and use pHStats. If you're looking at this and you don't have an option to it, you can look at this for the conceptual version of it. Due to licensing, I cannot release pHStats to anyone. So looking at this piece of it here, so those of you can run it, pHstat, regression, simple linear regression, and confidence interval. We did said in the last slide that That was our equation. And if we spent $310, that we would have $3,480 some dollars. Our prediction level is there. A little bit different than the last slide, but not enough to make much of a difference. And this is where this is different here. So these are written with macros. So for the average Y and for the individual response Y. So remember on confidence intervals that if we're looking at an individual value to do a confidence interval on, the confidence interval is much larger than if you do it on your average Y. So if on average we spend $310, we can expect to make between $3,000, I'm going to round here, $200 and $3,750 in sales. Now next week, if we spend $310, we can expect to make between $2,200 and $4,750. So if I were the manager of the store, I would say, okay, on average we spend about $310 a week, so when I do my budgeting for my staffing, I'm going to go ahead and use the fact that that's $3,200 in sales, or my high end $3,800, depending on how conservative or ambitious I want to get with it. Now, if I want to go, okay, next week's ad, this is what we can expect to make, and sales comes in at 2,600, did the model fail us? No, the model didn't fail us, because the next week we'll spend $310 and we might make 4,300. So because there's a little more variation in it, we just know that it's that unpredictable portion of life. So final reminders about doing this. The prediction model is limited to values within your sample area. We can use advertising costs between $105 and $605 because that was within our sample range. We can't use 800, we can't use 50. It's not causal. Just because we spend money on advertising, it doesn't mean that it causes sales. The model is based on a sample. So if I were to take the next 3 weeks worth of data and put it into the equation, my equation might change slightly. And it's only after the model is used and tested we really find out how valid the model is for prediction. It's that crystal ball effect that we're hoping to get as close as we can with it, but we know that there are factors that'll influence it. Hope this helps, and I'll catch you on the next lesson.